Welcome. Here we will give a brief introduction to our empty space research. The general concept of our work is introduced from the beginning until 4.14. The GapMiner demonstration begins at 4.14 and continues to the end of the video. In the vast landscape of high-dimensional data, empty spaces, regions where data points are absent, hold untapped potential. We show an intuitive metaphor to explain the concept. Imagine a 3D dataset like a piece of land. The collected data cannot completely fill the entire space, leaving behind empty spaces of various sizes. Some of them may not contain any meaningful data, while others might hold valuable information, like the gold in the land. The gold in empty spaces represents opportunities to uncover novel and innovative configurations that conventional methods often overlook. Whether in engineering, healthcare, or cybersecurity, discovering these hidden possibilities can lead to breakthroughs in optimization, design, and decision-making. However, identifying and exploring these empty spaces is challenging due to the sheer complexity of high-dimensional parameter spaces. This is where GapMiner comes in. Our system combines a novel empty space search algorithm, ESA, with human-in-the-loop visual analytics, guiding users through an AI-powered workflow that transitions from expert-driven exploration to AI-driven discovery. In this video, we'll describe GapMiner and show how it enables domain experts to efficiently navigate high-dimensional data, optimize configurations, and push the boundaries of innovation, unlocking solutions that were previously unknown and potentially unimaginable. But before we explore how GapMiner works, let's clarify a few key concepts. Target variable. In data-driven optimization, a target variable is the specific outcome we aim to improve or optimize. For example, in drug discovery, the target variable could be drug efficacy. In cybersecurity, it might be intrusion detection accuracy. Multiple target variables. Often, we don't optimize just one outcome, but several at the same time. For instance, in aerospace design, we may want to minimize weight while maximizing durability and fuel efficiency. This introduces the challenge of multi-objective optimization, where the system must find a balance between competing goals. Pareto front. When optimizing multiple objectives, not all solutions are equally good. The Pareto front represents the best trade-offs, solutions where improving one objective would mean sacrificing another. Identifying these optimal points is key to finding efficient and balanced solutions. Search space and empty regions. As discussed before, the search space is the vast landscape of possible configurations. However, not all areas are equally explored. Many remain empty simply because they haven't been tested yet. These empty regions might hold better solutions than what has been previously discovered. We call these solutions empty space configurations, ESCs. The ability to discover these makes empty space search a powerful tool for innovation. With these key concepts in mind, let's dive into GapMiner and see how it leverages AI and human expertise to explore and optimize high-dimensional spaces. GapMiner is a visual analytics system that helps users learn the dataset, explore the empty space, and progressively identify optimal configurations. It is composed of four major parts: the control panel, the overview display, the empty space configuration editor, and the progress tracker. The control panel enables users to load the dataset, split the target variable, configure the empty space search algorithm, choose a subset, and monitor the overview quality. The overview display is a PCA map that abstracts the existing configurations into density contours while plotting proposed configurations as scatter points. The overview quality monitor is the associated scree plot. The ESC editor provides a way to learn the empty space and fine-tune the configurations. The progress tracker monitors the reward and cost of the empty space search process, the performance of the neural network, and the quality of the dataset. We use a system simulation dataset for demonstration in this video. Each configuration in this system has 3 devices, L1, L2, and L3. Each device has 3 variables: size, average read latency, and average write latency. Since the size of the back-end storage device, L3, is fixed for all configurations, it is not included. Each configuration has 2 target variables: average throughput and purchase cost. Average throughput measures the performance of the configuration, while purchase cost is the price we pay for the devices in a configuration. We choose average throughput over purchase cost as the target variable, which means how much performance we get for every dollar spent. To use GapMiner, we first load the dataset via the file selector. The Pareto frontier plot shows the target variable distribution and Pareto front of the current dataset. Then we uniformly split a target variable into intervals using the target configurator. Thus, we can work on a subset of configurations with desired intervals through the ESC range selector. Upon checking a box in the existing group, the corresponding density contours will show in the overview display. By unselecting the Use Global PCA checkbox, GapMiner will perform PCA projection on the chosen subset only and plot the associated scree plot. The overview quality monitor shows that the PCA space doesn't explain much of the variance. That is to say, the configurations spread a lot in the original space, even if they gather in the PCA space. Now we dive into configuration optimization. First, let's run the ESA algorithm. Then we choose a desired interval and optimize a raw ESC via the ESC editor for demonstration. An intuitive conclusion from the overview display is that L1 size and L1 write latency contribute more to desired interval. So let's simply increase their values. The estimated result by DNN shows that it works, but not optimized to the Pareto front. Then we try to move the configuration to the dense region, since it is more promising to have desired target variable in dense region. Looking at the quality monitor, the PCA space doesn't explain much of the variance, so we must choose variables carefully. By referring to the PCA loading vectors and PCP-centered widgets, we increase L2 size, L1 read latency, and reduce L2 write latency. The verification shows it falls into the desired interval and close to the Pareto front. Next, we try to optimize a configuration from the Pareto front. We simply increase L1 size and L1 write latency since it's low in these variables and they are important according to the experience last time. Interestingly, the verification result shows that it works very well. The Pareto front extends significantly. Moreover, we can set constraints on the variables to search for promising ESCs in a subspace. For example, based on previous trials, we can set constraints on L1 size, L2 size, L1 write latency, and L2 write latency. Then we run an empty space search in this restricted region. The result shows it is promising for more exploration. Now we can verify a batch of ESCs. Once it's done, GapMiner automatically adds them to the dataset and retrain the DNN model. After all these done, one iteration finishes. Users can execute this pipeline to search for optimal configurations progressively. Finally, we show the results of the final stage, when the neural network is fully trained with the data. Now it can take the place of human experts to identify new empty space configurations autonomously.